Hey everyone, and welcome. Today we're going to dive into a pretty wild idea, something that feels totally backwards at first. Why, in the world of science, finding absolutely nothing can actually be a huge deal. Yeah, let's get into it. So let me ask you this. We always hear about the big wins in science, right? But what if an experiment just doesn't work? Or, more accurately, doesn't find the thing it was looking for? Is that a failure? Or could it be a success in disguise?
I mean, think about it. Ever since we were kids, we're told this story of science that's all about these huge eureka moments. An apple hits someone on the head, a guy jumps out of a bathtub yelling, Eureka! It's always about finding something new and exciting.
But here's the thing. The real, nitty-gritty, day-to-day work of science, the very foundation that all those big discoveries are built on, it often looks a lot less like a eureka and a lot more like, well, nothing. Just a dead end, a null result. So in this explainer, we're going to totally flip the script on what a failed experiment really is. You're about to see why finding nothing isn't just okay. It's one of the most important things a scientist can possibly do to move us all forward. All right, first up, let's just tackle this head on. We're going to bust the myth of the failed experiment. So here's the classic thinking. The myth is, if you don't get a statistically significant result, your experiment was a bust, a failure. But the reality, the thing that serious science runs on, a non-significant result is still data. It's an answer. The answer might just be no, and finding that out is incredibly valuable. And look, this isn't just some little pet peeve. It's a huge problem. This quote right here says it all. Even the experts, the people doing peer review who are supposed to be the gatekeepers of quality science, often get this wrong. They see a null result and think it's a flaw, instead of what it really is, a finding. So what's the fix? Well, it comes down to a really powerful idea called outcome-neutral review. And it's pretty simple, really. You judge the science based on how it was done, not what it found. And this is the absolute key. What makes a study good isn't whether the results were flashy or positive. It's all about the quality of the question and the strength of the method used to answer it. Seriously, a perfectly designed experiment that finds nothing is way more valuable than a sloppy one that just happens to stumble onto something. So what should reviewers be looking for? This right here is the checklist. This is the gold standard. Notice what's missing. Yeah, you don't see anything on here like, did it prove the big idea? Or were the results exciting? Nope. The entire focus is on the quality of the process. That's it. Okay, so if finding nothing isn't a failure, then what is it? We need to be super clear about what nothing actually means in science, because there's a really important distinction we have to make. Okay, this is so important. No evidence of an effect is not the same thing as evidence of no effect. I know, they sound almost identical, but the difference is massive. Think of it like this. The first one is like saying, I kind of glanced in this dark room and didn't see my keys. The second one is like, okay, I've turned on all the lights and searched every single corner, and I can now confidently say my keys are not in this room. See the difference? That difference between a quick peek and a thorough search is what scientists call statistical power, and this camera analogy is perfect. A low-power study is like a camera with no zoom. If you look at a faraway tree and don't see a bird, you can't say for sure there's no bird there. You can only say your camera couldn't see it. But a high-powered study? That's your super telephoto lens. It's designed to see even tiny things from way out. So if you look through that lens and still don't see a bird, well then you can be a lot more confident that the bird really isn't there. Power changes everything. So we've established that finding nothing is good, but what about when a study finds the exact opposite of what everyone thought was true? This brings us to another huge idea. Contradictions are actually amazing for science. We call these negative findings. They don't just find nothing, they actively contradict earlier research. And instead of being a problem, this is literally how science corrects itself. It's like the immune system for knowledge, weeding out ideas that seemed right at the time but just don't hold up. So why are these contradictions so crucial? Well, for one, they fight against something called publication bias. The pressure to only publish the cool, positive results. They're also the ultimate stress test for reproducibility. And finally, they force scientists to go back and make their theories even better. It's not about tearing things down, it's about building them stronger. Okay, let's bring it all home. How can we, whether we're scientists or just someone reading the news, get smarter about how we look at science? First, let's just know what the common traps are. These are the classic mistakes people make. like telling researchers to just keep digging in their data until they find something, or unfairly punishing a really well-done study just because it found nothing. Just knowing these pitfalls exist is a huge first step. And this right here is how we do better. It's a simple, powerful checklist for anybody. That first question is my absolute favorite. It's a little bias check for yourself. Would I be this critical if the study had found what I hoped it would find? This whole list just pulls the focus back to where it belongs, on the quality of the science itself. So, next time you see a headline about a new study, I want you to think about this. If it's some big, flashy discovery, ask yourself, but how are the methods? And if you see a study that failed to find a link, don't just scroll past it. Stop and realize that you might be looking at a quiet, powerful, and incredibly important scientific success. You might just be looking at the bedrock of how we learn anything at all.